welcome. In this class, which has multiple sessions, we'll explore how to do very simple numerical optimization with the goal of applying this to artificial neuron. The main concepts for this class are a function that has a scalar argument is a relatively simple function in mathematical terms. And what we'll do is we'll iteratively search for a minimizer of this function. This will require that we compute a hyperplane and initial estimate, and this is a fundamental algorithm for optimization. So the problem we can think of through this one is how can we find a function's local minimum with the ultimate goal of this function being an artificial neuron. So let's recall from basic calculus what a stationary point is. It means it's any point and any function where this function actually has to have certain conditions. It's what I call a nice function. What it means is that the derivative has to exist at that point and has to be equal to 0. So by derivative, that means that the left limit and the right limit all have to match up, etc. So a theorem for the first order condition is that if a value is a local minimizer of a function, then it has to be a stationary point. So you can think of a local minimizer as being think of something as being cupped upwards. That's called a convex function, and the minimizer has to be a stationary point. It has to be where the first derivative is exactly equal to 0. So let's go through some examples so that we can understand this a little better. Here I'm going to pick a function. I'm picking a rational function, so that's a ratio of polynomial functions. This turns out to have two stationary points. So this is what the function looks like. It will asymptotically approach 0 in negative infinity and 0 in infinity. On this limited values, it's not even close to 0. And it has two stationary points. So here it's got a stationary point that's at a local maximizer, and here the stationary point is a local minimizer. We could also look at the derivative and say, when is the derivative of this equal to 0? So here's the value 0, and here is one place that the first derivative is 0, and here's a second place that it's 0. And we could superimpose these and see that the 0 of the derivative matches this maximizer, the 0 of this derivative matches the minimizer. So stationarity is a necessary but not sufficient condition for something to be a minimizer. And we can see from this example that this is a stationary point that is not a minimizer. So a saddle point is something with a second order condition, and that is it has to be a stationary point, and it's not a minimizer and it's not a maximizer. So saddle points for scalar arguments are defined in terms of nots. That is, it's not something that is locally a minimum, and it's not something that's locally a maximum. A second order sufficient condition is that if something's a local minimizer, then its second derivative is always strictly greater than 0. So let's go through an example and see what this looks like. So now what I've drawn is a more complicated function. This is a higher order polynomial, and this function has three stationary points globally, and I focused in the plot so that we can see them clearly. So this point, it's a stationary point and it's a local maximizer. This is a stationary point and it's a local minimizer. And this stationary point, it's stationary because the derivative is 0. You can see the function is flat at this point. And it's neither a maximizer nor a minimizer. And this is what the first derivative looks like, is that it's 0 here, it's 0 here, and it's 0 here. This corresponded to our local maximum, this corresponded to our local minimum, and this corresponded to our flat saddle point. Now let's observe that here the second derivative is 0. That is, the derivative of the first derivative is 0. So that's a curiosity that we won't explore, but which we'll have to keep in mind for subsequent optimizations. And when we superimpose them, what we see is this is one of the stationary points maximum, this is another stationary point minimum, this is the third stationary point, and it corresponds to the function being flat, and a saddle That is, it's neither a local maximum nor a local minimum. So stationarity is necessary but not sufficient. Let's take a further look. So let's take a look at a really simple function, which is just the cubic function. So this function has one stationary point globally, which I focused in on, and you can see that it's flat. And when we differentiate this, the first derivative is 3 times t squared, and then the third derivative is 6t, and the second derivative 6t at this point, 6 times 0 is 0. So the second order test we'll say is inconclusive, and this would require further investigation. And again, this is something that we can look at in subsequent courses.